I'm going to introduce our article, Naval Cyber Physical Anomaly Propagation Analysis based on a quality asset graph. It was written with Pedro, Merino, Laso, and John Puentes. First, I will define the Naval domain in all of its specificities and constraints. Then I will introduce the related works to this article and present our approach and a case study to illustrate it. And to finish, a conclusion for the accomplished work, then a discussion for the perspective of our approach. So, naval systems are involved in crucial domains like passenger transportation, international trades, and of course, military activities. Whether ashore or aboard, their protection is a major challenge. And modern ships can be characterized by several systems, like the navigation systems, with several equipment that facilitate the monitoring and the control of the ship. There is also a communication system with satellite communication or information exchange with ship-to-ship or ship-to-shore communication. There is also a power management system that provides the high voltage for the power generation on board, a fuel management system for fuel monitoring and controlling, and of course, a propulsion management system, one of the most important systems on board that controls the propulsion modes with the engines and also the ballast system for the vessel stabilities. And all of these systems cannot be defined independently as an aggregation, but that they must be defined as interconnected systems that interact in several manners. And consequently, modern ships can be characterized as multi-layer networks formed by numerous interacting components. And for example, to ensure the propulsion of the vessel, the engine needs power from the power management system and also fuel from the fuel management system. And we will focus on these interdependencies to test our approach. So to securely ensure their mission success, ships must be aware of their environment and operating status. A vessel interacts with the physical environment through heterogeneous type of actuators and sensors, whereas the supervisory control system is increasingly digitalized. Consequently, a modern ship can be defined as a cyber physical system, a CPS. A physical process is monitored by sensors that collect data from the physical environments and transfer value to an embedded control program. And this program is running on a PLC, a programmable logic controller, that supervises and controls the physical process by making local control decisions depending on the input sensory data. A control variable is derived from this decision and sent to the actuators. This process is remotely monitored and controlled by the supervisory control and data acquisition system. Ships can also collect information through their communication system, but for this study, we will only focus on the physical process monitoring. And with all of this collected data, decisions are made by a human or material in a predictive and also in a real-time manner. And control variables are produced from this decision to modify the ship behavior. This collected data can be degraded by several factors and induce wrong decisions when anomalies propagate through the CPS. Consequently, it becomes necessary to detect anomalies and estimate the propagation in a suitable manner by taking into account the specificities of the CPS, all of these interconnection and possible propagation paths. Our work proposes to address these issues by defining a CPS-oriented graph model framework combined with data and information quality evaluation for anomaly propagation analysis. So our work gathers three major research domains: anomaly detection, anomaly propagation, and quality evaluation. To study anomaly propagation, anomaly must be detected before, and an anomaly can be defined as a data pattern that does not conform to the expected behavior. A lot of studies have been carried out to detect anomalies by applying statistic or machine learning to identify outliers, deviation, novelty, and exceptions. And because of the wide possibilities of targets, CPS constitute an autonomous model type to protect, and it's important to protect them. And despite the multiple possibilities to study anomalies detection, few works have focused on the problem of CPS anomaly detection. Most of them are domain specific and don't consider naval CPS. When the anomaly is detected, then you can study its propagation through the system. And anomaly propagation impacts different kind of connected system, but specific propagation models have been mostly developed for social network with fake news propagation and for computer or biological virus propagation. For the CPS, the existing models evaluate the consequences of an attack without considering its detection. Or other models have been developed to be domain specific, like for smart grids. And naval CPS have not been studied previously. And to respond to the issues previously exposed, so to detect anomaly and study its propagation, specific metrics must be studied for both. And because of CPS data-driven aspect, quality evaluation appears as a relevant metrics. And quality evaluation is an essential component of management information system, web information systems, and information fusion systems. Quality measures remains closely adapted to each application domain, and identifying a relevant method for a particular application must be difficult. Data information quality represents a major challenge for CPS, and few work have studied the application in them. This works mostly use quality evaluation for anomaly detection, but quality measures has not been studied for anomaly propagation analysis. And our work proposes to address these issues by defining a CPS-oriented graph model framework combined with data and information quality evaluation for anomaly propagation analysis. For our approach, so a graph is generated to identify the concerned subsystems as well as the interaction between them. Each subsystem is modeled as a node and each interaction has an edge. To meet the need of the CPS, which is a multi-layer network, the generated graph is defined with 2 layers. One layer for the digital subsystems that integrates networking and or computing capacities. The second layer for physical subsystems that interact with the physical process and transmit measured data or received control command from the PLC. And the third layers that describe the CPS current state with measured and control variables associated to each subsystems. This third layer is a major specificity of this graph modeling to focus on CPS variable dependencies. Dependencies of any variable at any time can be defined as a state correlation model. And we define 2 types of dependencies: structural dependencies. Structural dependencies. So structural dependencies is when a variable deviation can cause the variation of the others. And operational dependencies, when a variable deviation is subject to the activation of a specific values in other variables. And these dependencies can be found out during the system design process. However, it's not have been done. A conventional control modification could be applied to modify one variable value at a time and observe the impact of that change on the other variables. A graph is built accordingly with directed edges from the modified variable to the altered ones. And once the graph has been modeled, the next step consists on analyzing its components with graph theory. Such analysis provides an identification of the critical elements for graph-based anomaly propagation analysis. And for these studies, we applied a closeness centrality measures to identify which node is likely to have a high potential to propagate an anomaly. And the node with a high closeness scores has the shortest distance to all the other nodes. And in the next studies, other graph metrics will be implemented to improve this analysis. As data and information are constantly being exchanged between the subsystem of the CPS, in addition to the graph metrics, quality measures are assigned to each CPS system's variables. And these quality measures are dynamically assigned to examine anomaly propagation. For this work, we studied data and information quality measures. Each vector is composed of several metrics provided by the previous work on CPS quality evaluation, and only a subset of these given metrics is evaluated for each system. Anomaly propagation analysis is obtained from the observed fluctuation of the quality evaluation for each system's variable. And to test our approach, we chose to study one of the most critical systems on board, the propulsion management system. The systems control the main and the auxiliary propulsion modes, as well as the navigation heads. Our reduced propulsion management system is both composed of physical and simulated subsystems. The CPS is composed of 7 subsystems, including 5 physical subsystems, so a motor, a propeller, a valve, a fuel tank, and a hull tank, and two digital subsystems, a PLC, and the input-output module directly connected to the PLC. So the motor provides, through the drive shafts, required power to increase the propeller rotation speed, and this energy transfer generates an increase of motor temperature, and the valve is controlled to regulate the cooling and maintaining the systems at an optimal performance level. The increase of propeller rotation speed also causes a decrease of fuel and oil levels. There is also five systems variables associated to the CPS. There is 2 control commands given by the PLC. There is a propeller rotation speed command and a valve opening control command. And also, we simulated 3 systems variables: a motor temperature, a fuel tank level, and a oil tank level. And to simulate these systems variables, we use several Arduino single board microcontroller, which are implemented in the CPS prototype. These microcontrollers are directly linked to the input-output module to receive the PLC commands and transmit simulated sensors data. The CPS sensor behavior is emulated by generating analogic signals according to the received PLC commands, and the system's variables dependencies defined in the Arduino program. A Raspberry Pi is linked to the same Arduino, thanks to a serial port, to record the control command of the PLC and also the system variables that are simulated. And so there is a graph model of the studied CPS. Each CPS subsystems are modeled as a node, and while interdependencies are defined by the node, and we can find several types of interdependencies in our models. There is digital dependencies between the digital subsystems, and also physical dependencies between the physical subsystems. We can also find the sensor measurements from the physical subsystems to the input-output module directly linked to the PLC, and the control commands received from the PLC to the physical subsystem, donc, for the motors, for the propeller rotation speed control, and for the valve opening control commands. And of course, there is the dependencies between the physical subsystems and the system's variables, and of course, the dependencies between each system variables. And by analyze the studied CPS graph nodes complex, the graph analytics of this given graph give to us measures with the graph analytics to indicate that the motors and the input-output module and also the propeller rotation speed and the motor temperature have the highest centrality scores, and consequently, for the rest of the study, we only focus on analyzing the potential impact of anomaly propagation from these nodes. And as we said, both data information quality measures can be measured by making use of multiple dimension. And for this study case, we have chosen one metric for the data quality evaluation. It's the incomplete data imperfection, which is a set with a true value when supply data are not complete. And for information quality evaluation, it's more complex. It's defined by 3 categories: intrinsic for isolated subsystem, contextual for subsystems that are components of a more complex systems, and extrinsic to evaluate connected subsystems. Accordingly, our information quality evaluation is composed with one metric for contextual information quality and another metrics for extrinsic information quality evaluation. And once the system's graph model and associated quality evaluation metrics were defined, experimental tests were carried out to verify our approach. The quality evaluation process begins when the sensor receives data as an incomprehensible binary sequence. And next, information is defined when the data are decoded, by the corresponding protocol, and context gives a meaning to values. So there is 5 scenarios that have been examined: normal functioning conditions, port scan to detect all open ports, PLC stop to turn off the PLC, and 2 man-in-the-middle attack, one on the propeller rotation speed control commands, and another on the valve opening control command. So for the first generated anomaly, Nmap scan was run with a computer linked to the CPS digital network to find all the open ports of the CPS. The scan generated the numerous network package and provides target free entry ports, which are potential entry ports for further attacks. This attack was not detected, and the quality dimension of monitored systems variables were not altered. Then a stop command was activated to turn off the PLC, and consequently data information were not assigned to the system's variables of the propeller rotation speed and valve opening control. And we have noticed a quality evaluation alteration on all of the CPS subsystems because of the high interdependencies between them. And so the attack was detected. And to finish, we performed 2 man-in-the-middle attack. So the command value was modified on the digital physical layer connection between the PLC and the targeted actuators. Although the propeller rotation speed and the valve opening control were initially set at 50%, and the control commands were altered to 0%. And as shown on these schemas, the propeller rotation speed attack has had more impact on quality than the valve opening control attack. And so a modification of the propeller rotation speed implied a riskier anomaly propagation than the modification of the valve opening control. And of course, both of these attacks were detected. And to conclude, so the proposed approach is based on the CPS graph model that represents the physical and digital subsystems as nodes. And also a specific layer for this for systems variables dependencies was added. This third layer also includes a set of ocean data and information quality evaluations measures vectors that enable to detect anomalies and estimate the propagation through the connected nodes. Nevertheless, the system's variables dependencies are limited by their definition. For the experimentation, the obtained results are consistent with the preliminary graph analysis. The critical nodes identified by the closeness centrality measures correspond to those that showed considerable effects of anomaly propagation. And despite its simplicity, its experimentation, this first experimentation allowed to demonstrate the principle of anomaly detection and propagation estimation. And 3 out of 4 anomalies were detected, and the propagation was determined according to variable dependencies. And I said before, our methodology is focusing on physical process monitoring. And nevertheless, the post-scan attack was not detected. And to detect this type of network attack, we should implement quality metrics based on network package exchange, for example. And to study more complex CPS with a higher number of interdependencies, a complementary graph analysis should be applied. And for example, we can implement weighted dependencies and node dependencies, weighted nodes to enlarge the identification of potential anomaly propagation paths. And moreover, quality assessments will be completed with the knowledge and the wisdom concept to improve this anomaly propagation analysis. Thanks for your attention. And if you have questions, don't hesitate.
Thanks, Nicolas. Very interesting presentation. There are a few questions here where come up already. So Tim is asking, does your research aim to distinguish between intentional and accidental anomalies and propose different solutions according to the underlying cause of the anomalies?
Yes, so an anomalies can be intentional and not intentional. For example, an intentional with sensor dysfunctions and intentional with a cyber attack. So our approach try to meet the needs of the both aspects of anomalies and to detect also the intentional and unintentional anomalies. And thanks to data quality evaluation and quality evaluation in general, it's possible to detect these two aspects of the anomalies.
Okay. Anna instead is asking, what features are used for the detection process? Also, how environmental changes to sensors are rendered?
Can you repeat, please? I don't understand.
Oh, what features did you use for the detection process? And yes, how did you manage environmental changes to the sensors?
For the detection, so we use, I will find the slides. So we have several metrics based on quality evaluations to detect a fluctuation of the quality evaluation and associate it to the detection and the detection of an anomaly and to study its propagation through the systems. So both of the detection and the propagation analysis is based on the fluctuation of quality evaluation, and we record all of this data, and after we performed algorithm to perform these metrics, these quality evaluation metrics, to detect anomalies and study and analyze its propagation.
Okay, I think we have time for one last question very quickly. How did you inject the attacks? Did you use ICSS PLOIT or some other ways to inject the attacks to the PLC?
So we have 5 scenarios for the experimentation. For the port scan and map, PC is directly linked to the digital network of the SCADA systems. So we just inject a hand map on the network. And it's the same for the stop command to turn off the PLC. And for man-in-the-middle attacks, we modify the integrity of the values in the code of the Arduino program to inject the anomalies and to detect it after.